Okay, some more exciting reactions. Here we're going to be looking at cases where there's already two substituents on the ring, and so you'll have to consider two possible directors. All of these are kind of different situations that will highlight important facets of consideration. In this first example, we've got a methyl group up top and a nitro group on the bottom, and so we have ortho-para-directing and meta-directing. And so these are easy to predict because basically the substituents are in agreement on where the group should go. The nitro wants it meta from it, and the methyl wants it ortho or para. The para position's already been taken, so the only place for the bromine to go is in that ortho position, and it would be the identical spot over here. If we look at the next example, well, now we have two ortho-para directors. And so if we have two ortho-para directors, you have to know which one's going to be more highly activating. Alkyl substituents don't have a lone pair, so they're very weak electron donors. The OH group is a strong electron donor, pretty much the strongest one besides amine nitrogens. And so this will be a stronger one, and it stabilizes the positions ortho to it for reaction, or it activates those for reaction, more so than the methyl group activates its ortho positions. So in this case, the stronger donating group wins out in terms of controlling where the substituent is going to go. In the next example, here we have two identical groups that are ortho-para-directing. And so you would expect that, if it goes here, it's para to one and ortho to the other. Same case here. Or if it goes here, it's ortho to both. So all three of these positions are good in terms of electronic effects. However, what's observed whenever you have this 1-3 or this meta relationship of ortho-para donors is that you really only see the product where the group is ortho to one and para to another. Just due to steric crowding, it's unlikely that the chlorine would go to this position. It'd be harder for attack to occur there. And so these products are typically not observed. And again, that's due to the crowding nature. It's much easier to get here, and electronically, it's the same benefit. So it would take more energy in the transition state or the activation energy to form this. Our last example here, now we have two different ortho-para groups, directing groups that are meta to one another. And so we can get two different products. Again, electronically, they're in agreement. So if the nitro group is ortho to the hydroxyl, it will be para to the methyl, both good positions in terms of the carbocation intermediate stability. Or it could go here. It doesn't go between them for the same reasons. That would be crowding like that observed above. Now, one question after looking at this example, maybe you're asking, well, why can't the chlorine up here go to this position? Well, that would be the same molecule. It had the same name. And so it can go to that position. It's just the same molecule. Down here, when the substituents are different, these are different molecules with different properties. One problem that's good and has, I think, 4 more examples is problem 18.22 that you should take a look at. So next I want to move into something completely different. The other side of the aromatic substitution coin. Instead of electrophilic aromatic substitution, there's also nucleophilic aromatic substitution. These reactions are much more specialized and not as generally useful, but certain ones can be. And so we'll head into that right now. And this will finish up chapter 18. With nucleophilic aromatic substitution, you need to have a leaving group, just like we observed with SN1 and SN2 reactions. And so there'll be a halogen leaving group on the molecule, and we know how to put a halogen onto aromatic rings now through EAS chemistry. But so you're basically substituting a halogen. Remember, in all the electrophilic substitutions, you're substituting a hydrogen. It's an important distinction between the two. Very different reactions and mechanisms. In order for these reactions to work, you need a strong base / nucleophile, and so the most common, the best ones are the amide ion and hydroxide. Both of these strong bases, strong nucleophiles. And also anything related to these. So for example, an alkoxy ion like methoxide or propoxide can work. And any kind of substituted amide as well, for the same reasons. These reactions work best with electron withdrawing substituents. On the ring, and we'll see examples of that. And so it's the opposite scenario as EAS. Here, electron withdrawing groups activate the ring towards nucleophilic substitution, and that'll bear itself out in a mechanism. Well, there's two different mechanisms. There's an elimination-addition mechanism, and this is one that's just general. And so the elimination-addition mechanism occurs when you just have benzene or a non-activated benzene towards nucleophilic attack. So when there's no electron withdrawing groups, you'll have an elimination-addition mechanism. So when we say elimination, we're still talking about elimination in a classic sense, where you need a strong base. These reactions are carried out usually at elevated temperatures, especially when there's no electron withdrawing group on there. The first step is elimination. And so our ultimate product is a substitution product, and we maintain aromaticity throughout. But when we look at the mechanism, the first step creates this unique intermediate. And so just like similar to an E2 mechanism, we remove the hydrogen, the electrons from that carbon-hydrogen bond, move down to form another pi bond here, and the chloride leaves. Well, this action produces a strange intermediate called a benzyne. Intermediate. Well, now this triple bond, if it's sp hybridized, is really constrained because it's not anywhere near 180 degrees. So even though the aromaticity is maintained due to those bond angle or ring strain constraints, it's still highly active towards reaction. And in benzyne, now both of these carbons can possibly be attacked. And so first, your reactant acts as a base. And that's the elimination step. And then it acts as a nucleophile and forms bond to carbon. And so it can attack at either position, they're the same. If it attacks there, the pi bond that's not part of the aromatic system is lost. We get our hydroxyl group on. And then there's a negative charge at that carbon. And in the very last step, we need to take a hydrogen from somewhere. In the first step, we formed water, so that'd be the most logical acid in the solution. And we regenerate hydroxide. So first, elimination occurs to produce this unique benzyne intermediate. And this is a mechanism you'll need to know. So it's fairly brief, and it resembles things we've seen in the past, but it's much different than EAS. Elimination occurs first, then a nucleophilic addition, forming that bond to carbon to get our product. We can look at other examples of this. And so, for example, bromobenzene can react with sodium amide to make aniline. And so we have another pathway to aniline that does not involve a nitro group. The reaction is the same thing. You should draw out this mechanism for practice. It's a good one to practice. It will go through the same exact benzyne intermediate. You'll lose bromine. Amide will act as a base. Then amide will attack, acting as a nucleophile. So I would suggest trying to draw that mechanism out. I can check them for you later. Now, what if we have another substituent on the ring? Well, in this case, if we have this substituent here, in order to get elimination to occur, we've got to take a hydrogen from an adjacent carbon. So there's no hydrogen here. So the hydrogen will come from the other carbon, and that's fine. For clarity, we ought to use the other resonance form here. Well, strictly, it doesn't really matter. We want to be able to show that benzyne intermediate. And so the first elimination sequence occurs. and we get a benzene type intermediate. But now we have an issue. If amide attacks benzene here, then we'll get the anion that gets protonated to ultimately give us this product. But there's really no reason why the amide would attack here over this position. If anything, this one's more sterically favored. And so an amide can attack there as well. And it will. And you'll get a mixture. And so in this sequence, and the benzene would go up top. So either blue or red can occur. Give us this meta product as well. And then protonation gives us a mixture. And so when you carry out nucleophilic aromatic substitution, typically you can observe mixtures of products. In this case, we get an ortho and a meta. But it all depends on where exactly the leaving group was. And if there's a substituent on there, then the benzene is no longer identical in terms of the two carbons. And so each one can get attacked, you can get a mixture. And so this is a problem with the reaction. And so predict the product or products you would observe from this reaction. And this is another good one to practice doing the mechanism. You should pause it and try and predict them. The first one's always easy. Just going to replace the leaving group with the incoming nucleophile. And then, realistically, this is constantly in resonance, so either position is identical, and so you get the meta as well. So now we have a mixture of para and meta to the group that was already on there. So these all occur via this elimination-addition mechanism. The other mechanism happens when you have electron withdrawing substituents on the ring. This mechanism is not as important as the first mechanism. But it can be more powerful in that effectively you have a directing group on the ring, which controls the order in which things go on. And here, in a very similar reaction, notice we still have a group on there that's para. It's a chloro leaving group. Keep methoxide as the same strong base, strong nucleophile. But instead of an electron donating methyl group, we've got a strongly withdrawing nitro group in the para position. When that's the case, we get a single product, only para substitution, and it can occur at much lower temperatures at a faster rate because it has activated this ring towards nucleophilic attack. The nitro group stabilizes the intermediate, or one specific intermediate, that occurs in the mechanism. This will only happen, however, when you have a withdrawing group that is ortho or para to the leaving group. And so this addition-elimination mechanism is really pretty special. It has constraints on when it will occur. This is in the text on pages . And I'll only go over this mechanism, but you can see other examples in this region. The mechanism won't be surprising in terms of why we get stabilization, but perhaps the order that things happen might be a bit unique. Because of this electron withdrawn ring, the whole ring is more positive than in the other examples. And so the nucleophile can form a bond before the leaving group is kicked out. And unlike other substitutions, when it forms a bond here, since there's pi bonds, the leaving group doesn't leave immediately. And so we lose aromaticity. Because we formed an sp3 carbon. And so if we draw out the nitro group, this will be helpful in our understanding. From this position here, we want to consider resonance structures. And this will shed light on how the electron withdrawing group has to be ortho or para to undergo this mechanism. In the case when it's para, which would be the same as when it's ortho, notice the negative charge was put adjacent to where our nucleophile attacked. And it could have gone to either carbon, they're identical. But it'll be one away. Through resonance then, it can jump to the position para, which is directly stabilized by the nitro group. So the nitro group is stabilizing here because it's not a carbocation at this position, but a carbanion. So nitrogen is electron hungry. It can help stabilize that extra electron density that's right next to it on the carbon. And we can actually represent this with another resonance structure. So the nitrogen remains positive. It might be helpful to fill in arrows that show the movement of these electrons throughout these positions. And so we can actually draw this structure if that nitro group is ortho or para to the leaving group. And then, of course, we get one more that does not involve the nitro group. So we'll draw it up here. And so there's 4 total resonance structures. This one will just be convenient for showing the leaving group leaving. But when those electrons do come back and re-aromatize the ring, it's just by scooting over to form a pi bond. That pi bond is able to form because now we have a good leaving group that can be booted off. And so it's in that final process that we form the product. But here you can visualize the stabilizing effect of that nitro group. As the book will show, the more nitro groups you have, the more activated your molecule will be towards substitution. So for example, comparing these two examples, here we have an electron poor ring. This one's really electron poor, much more highly active or reactive. And so here we can selectively control replacement of that bromo because there's no benzyne intermediate. It'll just be first nucleophilic attack and then elimination at the last step to form the product. And so we can just replace it in that ortho position. Down here, this one will react in the same fashion. It's got a group ortho and one para to it, both of which can provide extra stabilization. And so we observe these as single products. If we're just comparing these reactions, this one would be slower, probably at higher temperature. This one would be faster at lower temperature. You could carry it out because it's doubly activated. Now, nitro groups are the most common substituents for carrying out these kind of specialized reactions, but they can occur with other electron withdrawing groups as well. Other electron withdrawing groups aren't as strongly withdrawing as a nitro group, and so they don't work as well or work as fast, but you can get them to occur, and there's some examples in the book problems. But this takes us through the rest of chapter 18, and it's a good stopping point.